We've gone through the mechanism of a bimolecular nucleophilic substitution reaction, SN2, but we haven't talked about unimolecular, stepwise nucleophilic substitution reactions. These are abbreviated SN1, substitution, nucleophilic, unimolecular. The rate determining step for these reactions is dependent only on the substrate. So let's give you an example here from before. Again, we've got a substrate with a leaving group. In this type of mechanism, enough activation energy is provided so that the leaving group comes off of the substrate. This generates a carbocation. We lose the leaving group, and then in a second step, a faster step, the nucleophile attacks the carbocation to give us the desired product. Again, because the first step in this reaction is breaking of a bond which requires energy, the rate of this reaction is dependent only on the concentration of the substrate. Another way to think about this is the nucleophile with a negative charge attacking a positive carbocation is so favorable that this second step is so fast it doesn't have any impact on the rate. So let's go through and draw intermediates for this reaction as well. In the first step, as the leaving group comes off, the bond between the carbon atom and the leaving group begins to dissociate. As this happens, we are generating a partial negative charge on the leaving group and a partial positive charge on the substrate. This is our first transition state. We will call this one A, and this will occur up here. As the reaction progresses, we generate our carbocation. That's why this is beginning to become positive. In the second step, we're forming a new bond between the carbocation and our nucleophile. So we have a new bond forming. Because the nucleophile is donating electron density, it is partially negative. And because the carbocation is gaining some of that electron density, it is partially positive. So let's label this transition state B, and this will occur here over the second step. So let's draw a reaction coordinate diagram for this reaction. Again, we're going to draw a plot where we have the potential energy on the left and our reaction coordinate on the right. Again, this reaction will be exothermic. So we're going to have our starting materials on the left, our products at a lower energy all the way on the right. And to fill this in over here, our product is the nucleophile added on to the substrate. Carbocation, leaving group with a negative charge, leaving group with a negative charge. So we have our starting materials here, our products over here. Notice, because this is a two-step reaction, we actually have a carbocation intermediate. In general, atoms don't like charge, or in other words, a charged species is going to be higher in energy. So if we've generated a carbocation intermediate, this will be a higher energy than either the starting material or the product. So I'm going to label this as our intermediate. How do we get to our intermediate? Well, we have our first transition state where the leaving group is being removed from the substrate. To do this, it requires a lot of activation energy. So it's going to take some energy to get up there and a slightly lower energy state to make our intermediate. Label this transition state A. As the reaction progresses, again, we're going to have a little bit of activation energy to have the nucleophile and the carbocation collide. So this second transition state B, which we will see here, will be slightly higher energy than our intermediate. And in the end, the new bond is formed, giving us back energy for the product. So again, we have two steps. The first step is here. The second step is here. An important factor to consider with SN1 reactions is how it impacts the stereochemistry. In an SN1 reaction, we generate a racemic mixture. So if we were just predicting the product here, we could say that we have the ethyl group the leaving group, the chloride, is replaced with the hydroxyl group. Our propyl group here, and our methyl group here. We also get the other stereoisomer. We get the enantiomer here, where the stereochemistry is reversed. So in the back we have our methyl group, and coming forward is our propyl group. Well, why does this happen? Let's think back to the mechanism. In the first step, the chlorine, the leaving group, leaves. When this happens, we generate a carbocation. What you should remember is that carbocations are sp2 hybridized, which means they are trigonal planar. So if we draw this a different way, we have an empty p orbital with a positive charge. We have our ethyl group here. The propyl group is in the same plane, and the methyl group is also in the same plane but going backwards. Because this is symmetric, our nucleophile, in this case the hydroxide, can either attack from the top face or the bottom face. Either way is equally likely. Because of this, we will get a 50% mixture of each of the two enantiomers. This is called a racemic mixture, where we have a 50-50 mix of two enantiomers. Finally, we have to talk about the substrate size and how that impacts the rate of an SN1 reaction. Unlike SN2 reactions, where the smaller the size, the more quickly the reaction will proceed, in an SN1 reaction, as the substrate gets larger, we actually see an increase in the reaction rate. This is because of two things. First, the inductive effect, and second is hyperconjugation. So let's take a look at two examples. We have this methyl chloride here, and we have a primary chloride here. Again, in each case we lose our leaving group, and we generate a carbocation. How do these carbocations compare? Well, again, let's draw them as a trigonal planar shape. And we'll draw the same thing for the other substrate, our primary substrate. And we're actually going to try to draw a little bit of stereochemistry in terms of the shape of this methyl group here. Again, remember, it's going to be tetrahedral. So what's the big difference here? Well, first off, carbon, because it's not very electronegative, can inductively donate electron density to the carbocation. What does that mean? The carbocation can draw some of the electron density from that methyl group, which will help stabilize that positive charge. So if we have more methyl groups or alkyl groups, we stabilize the positive charge by the inductive effect. If we have more stabilization, it's going to proceed more quickly because it's going to require lower energy to get to that state. Hyperconjugation is the other factor at play here. Again, remember the carbocation is trigonal planar. If we look at a methyl group attached to that carbocation, you might see that this bond here actually is in the same plane, or at least this bond can rotate so that the bond is in the same plane. And because of that, it can actually donate a little bit of its electron density to that carbocation. Again, if we're donating electron density, we're stabilizing it, and we're reducing the energy needed to generate that state. So we also have hyperconjugation in play. So a methyl chloride will basically never proceed through an SN1 pathway. A primary alkyl chloride will be the slowest. As we increase to a secondary substrate, we have two methyl groups which can donate electron density to our carbocation, and instead of a hydrogen here, we have another methyl group with another CH bond that can hyperconjugate with the carbocation. This will be faster. And finally, if we have a tertiary substrate, we have 3 methyl groups which can inductively donate electron density to our carbocation. That will also have 3 methyl groups which can be involved in hyperconjugation with the carbocation. So this will go the fastest. And again, energetically, this all boils down to the fact that if we have a tertiary substrate, the inductive effect and the hyperconjugation is going to give you the most stable carbocation. And a more stable state is easier to access, which means it will require less activation energy, and the reaction will move more quickly.